Hello, I have an interesting applet here. So let's bring in a positive charge. This is the electric field set up by a point positive charge. Let me bring in another negative charge. So this is the resultant field. Now I can add more charges, yeah? And I want you to see what happens to the resultant field as I add more and more charges. Now, does it occur to you that the resultant electric field between the two lines of charges seem to be straightening up? It seems that if I have two lines of opposite charges, I can create a uniform electric field in the region between the two lines of opposite charges. Let's look at another applet. So we have a positive charge and a negative charge, and the applet is showing us the resultant field. Obviously, this is not a uniform field. You can see that the direction keeps changing, and you also know that the field strength is strongest near the 2-point charges, and the field strength is also not constant along the line from the positive charge to the negative charge. Now, what if we line up a whole line of positive charges and a whole line of negative charges here? Meaning we have two oppositely charged plates. So let's switch the applet to two charged plates. So the applet is showing us the resultant field strength. So there's a line of positive charges here and a line of negative charges here. Do you notice that the field lines near the center of the plate seem to be vertically downward, and also the spacing between the field lines look quite constant? That's the signature of a uniform electric field. So it looks like if we have two oppositely charged plates, we can create a uniform electric field near the center of the two plates. Towards the edges of the two plates, you can see that the field line spacing gets bigger and bigger, so the field strength actually weakens near the edges of the two plates. So why am I showing you this? Well, I just want to impress upon you that if you line up two lines of opposite charges, you can produce a uniform electric field. So in practice, how do we create such a uniform electric field? Turns out it's very easy. You just need to find two metal plates, and then you connect a battery across the two plates. The plate that's connected to the positive terminal will have a layer of positive charges on the surface, and the plate that's connected to the negative terminal will have a layer of negative charges on the surface. And between the two plates, we can find out uniform electric field. So for example, if you have a plate here held at 6 volts and the other plate held at negative 6 volts, then you can create a layer of positive charges here and a layer of negative charges here, and this will produce a uniform electric field between the two plates. But I've told you just now that the field strength is actually weakening near the edge here and here. But in the A-level syllabus, we always make things very simple for you. You can just assume that the field strength is uniform everywhere between the two plates. And in the region outside the two plates, the field strength is 0. So that's how simple we make it for you in the A-levels. Now, since this is a uniform electric field, if you were to draw the equipotential lines, then the equipotential line should be evenly spaced out, right? So you got the 6 volt line here, and then 4 volts, and then 2 volts, 0, -2, -4, and then -6. If you sketch it out on a graph, how the potential varies with distance x. So x will be this vertical distance starting from the top plate. So the potential will start from positive 6 volts and decreases linearly to reach negative 6.0 volts across a distance of 4.0 mm. Yep, 4.0 mm is the separation between the two plates. Now, do you remember that field strength is equals to negative dV dx? And since dV dx is constant, we can calculate the field strength quite easily, right? So for this one, 12 volts, right? You have a 12 volts voltage drop over a distance of 4 mm. So it's just 12 volts divided by 4 mm, and you get 3000 volts per meter. You can find the parallel plates all over the place in electrical circuits. So I'll just use an example that's maybe more familiar to you, the cathode ray oscilloscope that you'll find in your labs, right? So inside every CRO, you will find two sets of parallel plates. What are they for, right? If there's no electric field, a beam of electrons will just travel straight, right, until it hit the screen of your CRO. But then we let the electron beam pass through two parallel plates. Like this set here will produce a uniform electric field that's downward. If I make you calculate the field strength, you just take 100 volts divided by the distance between the two plates. So we have an electric field that's directed downward, and since electrons are negatively charged, they will experience an electric force that's upward. Now notice that this force is going to be a constant force because the field strength is uniform everywhere throughout here, right? So the electrons will experience a constant upward electrical force as long as they are in the region between the two plates, which means they'll have a uniform acceleration that's upward. So which means the path taken by the electrons will be a parabolic path. It's exactly like your projectile motion, except that the acceleration is not 9.81 meter per second squared downward. The acceleration depends on the field strength. The acceleration will be the electric force divided by the mass of the electrons. After it has left the plate, it will travel along a straight line because the field strength is zero outside the parallel plates. So by adjusting the voltages we apply to the two plates, we can control where the electron beam lands on your CRO screen. Alright, that's all I want to say. Ta-ta!